Good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcoming Professor Nicholas Corrente. Professor Corrente completed his PhD in Chemical Engineering at Rutgers University in 2024 under the supervision of Professor Alexander Neymark. He is currently an assistant teaching professor in the Department of Chemical and Biochemical Engineering at Rutgers University, New Brunswick, New Jersey, United States, and the director of the Alchemy 3D Lab. His research focuses on adsorption in nanoporous materials and nanoscale thermodynamics, developing and applying molecular simulation methods to understand the relationships between structural, adsorption, and mechanical properties of nanoporous carbons and moths. His teaching and research efforts have been recognized through numerous awards, including the Engineering Governing Council Professor of the Year Awards from 2023 to 2025, and the 2025 Graduate Studying Research Award in Adsorption and Ion Exchange from the Separations Division of the American Institute of Chemical Engineers. So once again, welcome, Professor Corrente. Thank you so much for accepting our invitation. It's a pleasure to have you here with us. Please feel free to start your presentation.
Hello, everyone. As mentioned, my name is Nicholas Corrente. I am an assistant teaching professor in the Department of Chemical and Biochemical Engineering at Rutgers University. Today, I'm going to be talking about application of different methods for predicting adsorption-induced deformation in nanoporous materials. Before we get started, I want to make sure that I acknowledge everybody who helped with this effort. A lot of what I'm going to be presenting today was done during my PhD studies. And so I need to, of course, acknowledge the group members of the Neymark group. This was my family for many years, and we still work together to this day. Especially want to thank and acknowledge my advisor, Professor Neymark, now my collaborator, Dr. Shivam Parashar and Dr. Peter Ravakovich from ExxonMobil. This work was also contributed to by many undergraduate students. So Elizabeth Hinks, who's now a PhD student at Stanford University, Asta Casera, who's a PhD student at Northwestern, and Raleigh Goff, who works for a company called Medtronic. And then, of course, our international collaborators, Professor Zarebska from Poland, and Dr. Jinlu Liu, who's at Halliburton. And of course, the Atoms group for giving me this invitation. And then this work was also funded by the National Science Foundation, ExxonMobil, and Rutgers School of Engineering. I want to tell you a little bit about Rutgers itself. So we are a university in New Jersey. We're about 60 kilometers from Manhattan, about the same distance from Philadelphia, right in between. Our university was established in 1766. We are the 8th oldest university in the US. Rutgers has 3 campuses. We are the main campus in New Brunswick, where we have about 38,000 undergraduate students, 12,000 graduate students. You can see down here, this is our Hall of Engineering, one of our newest buildings we're very proud of. And today, now getting into the material, as I said, I'm going to be talking about adsorption-induced deformation. So it's necessary to really discuss what this is. Adsorption-induced deformation is a phenomena where when we have particles that adsorb on a surface or in a nanoporous material, they cause deformation of the material. And this deformation doesn't happen in a way that some would typically expect. When we have a pore space with low loading of molecules, each of those molecules is attracted by opposing walls in the pore space. And this opposite attractions causes a negative stress to be induced in the porous material itself. And these molecules end up as molecular springs that are pulling on the walls, causing a contraction of the pore space. As we increase adsorption and then the adsorbate becomes crowded inside of the pore space, That negative stress switches to a positive stress, where this dense fluid is now pushing out on the walls, and this causes an expansion. So we see this non-monotonic trend in adsorption with many different materials. And it turns out all porous materials undergo this adsorption-induced deformation to some extent. And really the magnitude of this effect is governed by the stiffness of the material. Materials that are more flexible see a huge deviation in their volume, and materials that are stiffer do not. So for things like carbons, we can see 5% deviation in the volume. For things like metal organic frameworks that undergo breathing transitions, this effect of deformation can cause huge differences in swelling and in volume. So we can have a change in the volume from 30% to up to 80% in some metal organic frameworks. And so we want to have ways to account for this deformation phenomena. And this is really going to be the point of the talk today, in order to figure out ways that we can predict this phenomena. So I'm going to start, as the title of the talk suggests, with thermodynamic models. We're going to look at theoretical adsorption equations and applying those to predict adsorption. So I'll talk about that section very briefly. And then we'll talk about classical density functional theory and how we can use this to predict the deformation in a porous material. And then we're going to transition over into atomistic simulations. And this is the area where we're working right now, which is developing simulation methods to be able to predict deformation of atomistic structures, atomistic models. So in order to talk about this thermodynamic model, it's necessary to introduce the model that we used for approximating this deformation, this adsorption stress model. So we consider our system as an adsorbent with a volume V in equilibrium with a gas mixture. And we're looking primarily at mixtures because most engineering applications involve mixtures. That gas mixture has a given composition at a specific pressure and temperature. The way that we characterize the adsorption-induced deformation is with this adsorption stress. So this adsorption stress is the negative derivative of the grand thermodynamic potential with respect to change in volume at constant chemical potential and temperature. So we are looking at how this thermodynamic potential changes when we change our volume. We can get this, we can access this thermodynamic potential by looking at the theoretical isotherms, and specifically looking at the integral of the theoretical isotherms of the adsorbent in our structure. And we trace the trajectory very carefully. So we go ahead and use this approximation for the properties of our gases and equation of state in order to link the chemical potential with our pressure. And then we chase the trajectory of these theoretical isotherms from low loading at very low pressures up until our pressure of interest. And if we take the chemical potential as a function of the composition of each of the species, then we can link this pressure and this chemical potential. The question here is, how do we get these theoretical isotherms? So these are the isotherms of our rigid sample. So taking this isotherms of our rigid sample and using those to approximate what the stress would be. Once we know the stress, then we can approximate the experimentally accessible values, this deformation or this strain, by using this simple harmonic approximation, where we use Hooke's law, knowing the modulus of our sample. And then we take, of course, the difference between this adsorption stress and our external pressure. So we get this so-called disjoining pressure or solvation pressure, which is this difference between the adsorption stress and our external pressure. So again, the question here is, how do we get our theoretical isotherms? One way is to take a look at experimental data and use some adsorption model to fit that experimental data, and then we can access this grand potential. And that's what I'm going to show at the beginning, two applications of this Langmuir model. I'll go through this very quickly, so that way we can get to the for many people, I think, more interesting talk, which is using density functional theory and molecular simulations in order to access this theoretical isotherm. So as I said, we can use this Langmuir model to predict our adsorption isotherm. And the key here is we can use a binary Langmuir model fitted to our pure component isotherms, and then using just thermodynamics and thermodynamic relationships, we can access the grand thermodynamic potential from that adsorption isotherm. We get a nice expression for our thermodynamic potential, and then we can take the derivative of that thermodynamic potential with respect to volume, and we end up being able to access these changes in the Langmuir parameters. So our change in our adsorption capacity and change in this Langmuir parameter, this energy of adsorption term. And we introduced in this paper that we published in 2021, this susceptibility factors. So how these parameters change when we change our volume. And what we see are very interesting, very intuitive trends. As we increase our volume of our sample, we increase the pore space. And increasing that pore volume allows for an increase in the amount of adsorption because we have more space to fit adsorbates. But we also see a decrease in the energy of adsorption as we increase the volume. As our pore walls are spreading out, as they're getting farther away from each other, the overlapping attraction between the walls diminishes. And so the adsorbate molecules are attracted less strongly into this sample. And so when we go ahead and fit, for this paper, for this work, we fit pure component isotherms for adsorption of carbon dioxide and methane in coals. And we saw exactly what we expected, this increase in our adsorption capacity with increase in volume, but a decrease in the energy of adsorption with increasing volume. And this model allowed us, with just the pure component isotherms, to predict adsorption of mixtures of these two. And we found very good agreement between our experimental values that we had from our collaborators and the values given from our model, to the point where for many of these points, you can actually see the difference. They overlap. I'd be happy to take questions on this, but I'm going to go through this very briefly. One thing I will say about this is that this model is, the idea here is developing this theoretical framework. And the nice thing is this theoretical framework is transferable. We can use it for any situation where we have pure component isotherms and then an isotherm for a mixture. And so what we did is we actually applied this to adsorption of carbon dioxide and methane in metal organic framework, MEL53, this metal organic framework that I showed at the beginning that undergoes these huge breathing transitions. So MEL53 is known to transition from this large pore structure. This is its default state at low pressure. Once you have a strong enough attraction between the sparse molecules at low loading in the structure and the structure itself, you have this collapse into this narrow pore phase. And then as you increase the loading even more of your adsorbate, you see this transition back to this large pore phase. So you have this interesting trend where you collapse and then expand your volume. But the interesting thing here is that this transition is dependent upon the composition of the gas. Methane, for example, at 298 Kelvin, introduces enough of a stress where it undergoes the one transition, but it doesn't undergo the other. So it doesn't go back to this. I'm sorry, methane doesn't undergo the end transition at all. It stays in this large pore phase. So there's not enough attraction between the methane molecules and the metal organic framework to introduce this transition to the narrow pore phase. Once you introduce carbon dioxide to the equation, though, either pure carbon dioxide or a carbon dioxide methane mixture, then you start to see this transition from the large pore phase to the narrow pore phase. So carbon dioxide is strongly attracted enough in low loadings to collapse that structure into the narrow pore phase, and then to induce the transition back to the large pore phase. But that transition is a function of the composition. And so what we did was we applied this binary Langmuir model, in order to predict where we would experience this transition. And we found that we had great agreement, again, between the experimental values and the values for this transition point from our model. And so this framework that we developed that uses this Langmuir model is transferable between carbons, which undergo mild to moderate deformation, to these metal organic frameworks, which experience these huge breathing transitions. So the issue here with using this framework is that it's often very difficult to get the experimental values that are needed in order to apply this model, because it requires your pure component adsorption isotherms and your pure component strain isotherms. And measuring these two in tandem is difficult. It requires special equipment in order to do this. And so what we wanted to do was look at another way to predict the adsorption of mixtures. And so we turned to density functional theory. There are several works that use Leonard-Jones adsorbates in simplified or cylindrical pore shapes in classical density functional theory, but usually those are restricted to pure calculations because the Leonard-Jones model is not great at predicting mixtures. And so what we did instead was look at using a more representative DFT model, representative equation of state that can predict mixtures. And so we turned to this PC-SAFT model. And this is actually where my first interaction with the Adams group happened. So as I was preparing this talk, lucky enough to find a rather old screenshot of our group and the Adams group, so the Neimark group and the Adams group, where Fred and Gabrielle Barbosa were nice enough to give us a seminar on how to use PC-SAFT coupled with density functional theory for doing adsorption calculations. I apologize to everybody who's pictured in this slide. It's not a very flattering image, I think, of any of us. But I can tell you that this seminar was transformational for my work as a PhD student, both because it introduced me to an even greater understanding of how DFT works, but also because at the time I was working on a code that we had been collaborating with, that I had been playing around with, and I had an error in my code for weeks that I could not figure out. And as Gabrielle was presenting the equations, I ended up finding this during the talk. So I tell Fred and Gabrielle every time I see them that all of the work I do with DOT was only possible because of this seminar that they gave to us. So let's talk about this PC-SAFT model. Why is it so good? So PC-SAFT, like many models, starts with this free energy. So it looks at the free energy of the system and free energy of the, in this case, the adsorbate, as a combination of different terms. So we, of course, have the ideal gas term. We move on to the hard sphere term, which is inherent to many of these spherical Leonard-Jones models. Where PC-SAFT is a little bit different is it takes these hard spheres and binds them together as chains. And so you have the ability now to look not just at spheres, but also introduce this shape of the molecule and account for branching or chain molecules. And these chains are interacting with dispersion interactions. And so this PC-SAFT model then has different terms. So we have the segment number M, we have our segment diameter sigma. This is the same between PC-SAFT and something like a Leonard-Jones sphere. We also have our dispersion term, which is the same between the two, and we use a slightly modified mixing rule in order to predict better the mixtures. I would invite anybody who has any questions on this. There's a lot of work, a lot of opportunity for further reading here. And this is actually the best time to get into classical DFT work, especially SAFT DFT work. There's many publicly available codes that are incredibly efficient from the Adams group, from Gross's group. So if you are considering getting into DFT, now is the time to do it. So what we do then, what we were interested in looking at, how can we use PC-SAFT to predict adsorption in simplified pore shapes, in these slit, cylindrical, and spherical pores. So we did this using this in-house code that I was working on that we had been given from Jinli Liu from Walter Chapman's group. And we were looking primarily at carbon dioxide and methane in carbon nanopores. The idea here is taking this example of carbon dioxide enhanced natural gas recovery as a test case. But again, this sort of framework can be used for many different systems. Important here is that we took atomistic representations of our pores and converted them to a continuum representation with the Steely potential for slit pores and then modified potentials for cylindrical and spherical pores. And as I said, this PC-SAFT model allows us to take molecules with different shapes other than just spherical molecules and account for those shapes. So we, for example, when we go from an atomistic CO2 representation to a CO2 representation in this version of PC-SAFT, we get a molecule that has 2 and some change beads in it. And we can see this here. So we can start to account for the shape of these molecules too, not just the size of them. Because we don't have great experimental data, what we took as a test case here was grand canonical Monte Carlo isotherms. So taking slit pores in this case in density functional theory and comparing to grand canonical Monte Carlo simulations of carbon dioxide and methane in their mixtures in slit carbon pores. And what we see here is that we get excellent agreement for different pore shapes, different gas compositions between our density functional theory adsorption isotherms, these are these lines, and the points from grand canonical Monte Carlo simulation. So this is fantastic agreement across all pore shapes that we considered. The key here, though, is that this is achievable in a fraction of the time. So when I first did this, did these calculations in density functional theory, it took about 25 minutes to run an adsorption isotherm of 200 points in a 1.5 nanometer pore. The codes have gotten so good that I can run this now in about 2.5 minutes. This is compared to, and these are, by the way, all in serial. Each point follows the next. This is compared to about 2 hours for one pressure point in grand canonical Monte Carlo. So we can achieve the same level of accuracy for the simplified pore shapes in a fraction of the time. What we did, though, so again, the goal here is to be able to apply this thermodynamic model to predict the adsorption stress and the adsorption strain. And so what we did was we took a look at what happens if we change the pore size slightly. What happens to the adsorption isotherm? And what we can see is if we take, for example, pure methane or pure carbon dioxide, and we slightly increase the pore size, so from 1 nanometer to 1.04 nanometers, we see a slight but significant difference in the adsorption isotherm. And a real interesting trend emerges. When we have lower loading, when we increase the pore size, we get lower adsorption. So this is this region where this energy of attraction term dominates because your adsorbate is adsorbing onto the walls of your structure. And so as you increase your pore size, you decrease the energy of adsorption. And so you see a decrease in the loading. As you densify your structure, as you fill your structure with more adsorbate molecules at higher pressures, you see that trend flips. So the larger pore size is able to accommodate more molecules. And so you have this increase in adsorption in the larger pore. Now, this relationship between adsorption isotherms at slightly different pore sizes is a way that we can probe this derivative of the grand thermodynamic potential with respect to volume. And so we can estimate the adsorption stress by using a finite difference method. So calculate with DFT your adsorption, your adsorbed amount in different pore sizes, And then you can predict this derivative. You can also do this in DFT by accessing the grand potential directly, which is a very nice feature. And you get similar results. So for this work, for everything I'm going to show today, we use a center difference approximation. So for each adsorption isotherm, we predict 3, one at a higher volume, one at a lower volume, in order to calculate our adsorption stress. What we see when we put this all together, and keeping in mind that we're looking at here the salvation pressure, this difference between this adsorption stress and this external pressure, what we can see is some really interesting trends. So for example, if we look at these purple curves, these are the pure methane curves, we have, in all cases, lower magnitude of deformation in pure methane as opposed to pure carbon dioxide. And when we start to introduce more carbon dioxide, when we increase the fraction of carbon dioxide, we see almost invariably an increase in the contraction at low loadings, and then increase in the expansion at higher loadings. And so this happens for 1 nanometer, 2 nanometer, 3 nanometer, and 5 nanometer pores. An interesting thing that we see as well is that this magnitude of this effect is a function of the pore size. Smaller pores experience larger contraction and larger expansion as opposed to larger pores. And this makes sense when we have pores that are very small. The molecules, the adsorbate molecules, are pulling on both walls at the same time and pushing on both walls at the same time. And so they introduce larger negative stress and larger positive stress when you go from this contraction to this expansion. As we increase the pore size, now we start to get this dense region of fluid in the middle of our pore, and that dense region of fluid, I'm sorry, it's not dense, it's a bulk region of fluid, a bulk-like region of fluid in the middle of your pore. And that bulk-like region of fluid is only really pulled on one wall or the other. It doesn't feel the effect of both walls as strongly as in smaller pores. And so the stress of the negative stress and the positive stress are correspondingly lower. Interestingly here, so we have this trend from DFT. What we also did was we wanted to see how does it compare with grand canonical Monte Carlo. So a wonderful undergraduate student, Asta Casera, ran many grand canonical Monte Carlo simulations in order to get this plot. And what we see is we get a decent qualitative match between the solvation pressure and our strain predictions from DFT and from our grand canonical Monte Carlo simulations. But again, this DFT, the DFT data on this plot takes 10 minutes to run. The grand canonical Monte Carlo simulations, each of these series of points is 3 simulations. So this took her a month to run, probably a little bit longer. And so we can access a similar level of accuracy with these DFT models in a fraction of the time. There is some deviation, and some deviation is likely to packing. There are some simplifications in the way that DFT is able to orient molecules. And so having a more representative DFT model to account for rotations might be helpful, where there is some steric hindrance in how the atomistic models can pack in our pores, but overall this is a really good result. So looking at this, we wanted to know, we saw that we can apply the DFT model for these systems, but if we have this much more efficient method, then can we leverage that more efficient method to learn more detailed adsorption effects? So everything I've shown up until now was published in this paper in Journal of Physical Chemistry C. We were honored to be selected as the journal cover art for this issue. And we wanted to see how big can we get? How ridiculous can we get? How much can we calculate? And so what we did was just run an absurd amount of adsorption isotherms. So this plot is a small collection of what we ended up running. So we ran over 100,000 pore sizes. This is just an exercise in insanity at this point, just seeing what we can do because these calculations are so efficient. This plot is a scary looking. What I want to do is just draw your attention to the highest pressures. And we can see if we look at the colors that we have some interesting trends that are going on with our pore size. It looks like there may be some sort of fluctuation. So what we did was we took the adsorbed amount at the highest loading and plotted it as a function of pore size. And we also calculated the solvation pressure in the same way that we showed before. And we saw this really interesting trend, which is well understood in the literature. This has been known for a long time, that if you have a slit pore, in this case, we have methane and slit pores. If you have a very small slit pore that can accommodate one layer of molecules, you have a very densely packed system. If you slightly increase your pore size, you now can fit a little more than one layer, but not quite two layers. So you go from a commensurate pore to a so-called incommensurate pore shape. And now your loading, where you're trying to fit additional molecules, is complicated. It's no longer very ordered. And so what you see is when you have these very ordered structures, you have these peaks in your density. As you increase your pore size slightly, you fall. So for example, if we had 1.5 molecules, when we increase our pore size even more to get to the point where we are able to accommodate 2 layers of molecules, then we get this much denser structure. As we increase, we get still this fluctuating behavior in our density. And this diminishes as we get to larger pore sizes because of this development of the bulk region in the middle and because of the diminishing attraction with the walls. We also see, as we look at the solvation pressure, we see a very similar trend. These much more ordered states are able to pack much more ordered, and so they're able to induce larger stresses on the walls. So you can see this as a progression of pressure if you take a look at the color map on the right. And we can see as we increase our pressure in our pore size, our commensurate pore size here, we increase the solvation pressure and would see a corresponding increase in the strain in our system. As we slightly increase the pore size, so we can fit not more than one layer, but not quite 2 layers, we disrupt this loading. And so we also see a disruption in the expansion. And so we have this negative stress now, this contraction of our pore size. As we get to this 2 layers structure, then we see this increase in our solvation pressure that corresponds with this increase in our density. So this is a really interesting trend. Again, it's well appreciated in the literature, but what's nice about DFT is we can also look at this now, look at all of the variables associated with this. So in the PCSAFT, the standard PCSAFT model, our methane molecule is described with a sphere. And so if we go ahead and take a look going from methane to ethane, even though we get lower loading of ethane, we see this behavior as well. Ethane is a approximately 2-center molecule now. And so we get stronger adsorption, and we can see this on the adsorption isotherm, and we get a corresponding stronger expansion and contraction. So stronger stresses that develop in our system because the molecules are attracted more strongly to the wall. We can see this even more as we increase to propane. So even though we have a reduced loading of propane, each of these propanes has an increased number of attraction sites, we get stronger adsorption in our system and much stronger expansion and contraction. So we actually increase the solvation pressure over the systems that we had before. Now, this is the really interesting thing. The question here is what happens if we have mixtures? So if we take that system that we started with, methane and carbon dioxide, when we look at a equimolar mixture of methane and carbon dioxide, so equimolar in the bulk, we can see that we disrupt now this sort of this layering that takes place. And so we don't have quite as neat fluctuations in our plots as we did before. And this is because we now have two molecules with different shapes that are trying to pack. And so we see packing effects. So we see these strong peaks with carbon dioxide. Carbon dioxide is attracted more strongly to the carbons than methane is. And we saw this through the original work as well. And then we also have these intermediate peaks where we have this methane, and this methane is disrupting the packing of the carbon dioxide molecules. And so we can see these additional peaks that show up on this plot from this methane carbon dioxide competitive adsorption. What we can also see as we change our pore shape, when we go from a slit pore where you're able to accommodate nice layers to a cylindrical pore, now you have to worry about your curvature. And so you can't pack your molecules as nicely. And so we have this disruption in our loading, and a corresponding disruption in the nice even peaks from our solvation pressure. But our slit pores also, now we have stronger attraction between opposing walls because of the shape of the pore. And so we do see that we have some attraction, but the magnitude is not quite as high as the solvation pressure for the slit pores, because we don't have this nice even layering. And this is complicated even further when we go to a spherical pore. So if we look at methane in spherical pore, we've pretty much entirely diminished this fluctuating behavior. We see a smaller solvation pressure because in spherical pores, it's just very difficult to accommodate these nice even layerings. So commensurate pore sizes in slit pores are very difficult to achieve. When we go for really small pores where we can fit one sphere, we have a very large density and of course a very large solvation pressure, but then that diminishes monotonically as we increase the size because we can't pack the molecules as well. I will just briefly discuss here, DFT is not just for 2D structures. It can also be used for 3D structures. So this is an example of what I'm going to show next in 3D carbons from a 3D DFT code from the Adams group. And we see that we get excellent agreement between 3D density functional theory and some Monte Carlo results, which I'm going to show in a minute. So DFT is not just for 2D. It can also be used for 3D structures. And you see a similar increase in efficiency for calculation from DFT than you do for over GCMC as you do for the 2D structures. So just to wrap up this one section very quickly, the thermodynamic model allows us to predict what would be the adsorption deformation in these simplified pore structures. We show this with DFT and with these theoretical models. What we want to see next is how can we go ahead and account for a more realistic pore shape? So far we have only used slit and cylindrical and spherical pore shapes, but carbons themselves are very disordered. They have interconnected pore networks, broad pore size distributions, and so can we use 3D porous models with atomistic simulations to account for this deformation? The key here, though, is it's a little bit tricky to figure out how to use this thermodynamic model. And so what we can do instead is develop a simulation, a molecular simulation model to predict this deformation. So very quickly, the question here would be, why would we care about these 3D models? Well, it's because these 3D models allow us a tunable way in order to get different structures of different surface areas and porosities using the same generation procedure, just by changing the density of the carbon in our structure. And so we can get these models to fit various experimental carbons by just changing the density. And for further reading, if anybody's interested, we recently published a review on the molecular models and density functional theory methods for predicting adsorption and deformation in carbons. I would be happy if you all went and read that. I'm going to very quickly focus just as an example on this one carbon. So this carbon, we found in a different publication that this carbon gave us quantitative predictions to a reasonable degree of accuracy for a whole bunch of different adsorbates. So we saw this one carbon model using standard parameters for different adsorbate molecules gave us excellent agreement with this no-RIT R1 extra experimental results. So these are small, simple molecules like nitrogen, carbon dioxide. We even saw a somewhat qualitative agreement with a polar molecule, SO2, not quantitative because these are purely carbon models. So dealing with polar functional groups is not quite there yet, for these at least. We also saw for alkanes, we got excellent agreement for smaller alkanes, both in adsorption and in heat of adsorption, in isosteric heat. So these 3D carbon models present an interesting area to explore. Can we use 3D carbon models, maybe with some functionalization, to give us more reasonable predictions for experimental structures? So what we wanted to do was take a look and see, can we use them to predict deformation? Those models that I showed before are a little bit large for a test case. And so what we did was we generated our own models using this environmental dependent interaction potential for carbons developed by Nigel Marks. We matched the density of that carbon from the previous slide, and then we generated also another test case with a much more open pore structure. So we have a purely microporous carbon and a microporous carbon with some small mesopores to take a look at the effect of the density of the carbon and the pore size and on adsorption and deformation. Once we generate our carbon models, then what we do is develop a procedure where we can adsorb molecules on the structure and allow the structure to deform in response to that adsorption. So we take our rigid structure and adsorb molecules in grand canonical Monte Carlo simulations. This is the standard procedure for adsorption calculation. What we then do is use that same EDIP potential, the flexible potential for the carbons, and we fix the number of molecules in the structure from the GCMC run, pass it off to a molecular dynamics simulation where we allow the structure to deform to accommodate those molecules. And we just do iterations of this procedure. And what we ultimately get is the ability to look at, of course, the rigid isotherm from standard GCMC and compare it to a flexible isotherm from this hybrid simulation scheme. And so we can see for different structures, does introducing this flexibility matter? And does it give us any appreciable difference in the amount of adsorption and the amount of strain? What we see is on the left here, we have adsorption isotherms. On the right, we have the strain isotherms for each of the structures, that much denser 1 gram per cubic centimeter structure in orange on the left, and then this much more open 0.5 gram per cubic centimeter structure. What we see is that when we introduce flexibility in this more open structure, we see a large strain. So the structure is much more flexible, it's much more open, has larger pores, but that strain, that expansion and contraction, does not actually contribute to a marked increase in loading as compared to the more rigid structure. And that's because those pores are larger. You have that looser bulk-like molecules in the center, which have this weaker attraction to the walls. Whereas in the smaller, this more closed structure with a larger carbon density, so these smaller pores, introducing more space to accommodate molecules increases this stress quite a bit and also can increase the amount of absorption quite a bit. So even though we see a lower expansion in our more dense carbon structure, we see a relatively larger increase in the amount of adsorbed molecules because the slight change in that pore size opens up space for new molecules to fit closer to the walls. What we also see when we looked at a comparison between adsorption in methane and carbon dioxide is exactly what we expected to see from our simplified pore models. When we introduce carbon dioxide into our system, when we have pure carbon dioxide, we see a larger amount adsorbed over methane. When we have a mixture, increasing the fraction of carbon dioxide increases the adsorption. And just like we saw with the density functional theory calculations, increasing the amount of carbon dioxide increases the magnitude of the contraction and the expansion. Because carbon dioxide is more strongly attracted to the carbon walls, introducing carbon dioxide induces larger negative stress to contract your system and larger positive stress to expand the system. And so we see the same trends that we saw with the simplified thermodynamic model, where we're not actually deforming anything, just doing a thermodynamic prediction. We see a direct correlation here, where we have this same trend showing when we're directly simulating the adsorption of these molecules. So two different ways to do these predictions offer the same trends, which is very exciting. Just like we can transfer the Langmuir model framework from carbons to moths, this hybrid scheme is also transferable. Any flexible framework that you have a potential for, you can run these simulations. And so we, Shivam Parashar, Alex Neymark and I published a paper this year looking at this deformation in Iremov-1, this metal organic framework. Iremov-1 doesn't undergo very large swings in pore size, but what we do see is that introducing this flexibility allows us to achieve a better fit with experimental isotherms than this rigid isotherm has. So even very small strain, so less than 1% deviation in our volume, can give us a marked increase in accuracy of our simulation methods. And with that, I'll conclude this part about this molecular simulation model. So we saw this ability to directly observe the structural evolution during adsorption. And what we'd like to do is, and what we're able to do here too, is also access some of these thermodynamic properties. And so we can look at how the strain or the modulus of our structure, for example, changes. How stiff does our composite structure, this carbon with adsorbed molecules, how does that stiffness change when we put molecules inside? And this scheme allows us to predict more reliably the performance of flexible nanoporous materials at different conditions that we're interested in. And we can also, as I said, extend this framework, extend this simulation scheme to many different classes of materials. So as long as you have intermolecular and intramolecular potentials for your adsorbate and adsorbent molecules, you can run this scheme on any system. And there I'm going to conclude my talk. I again want to thank everybody.